Hello, good afternoon, everyone. So, today we will start the week 6 lectures. So, we will just wait for 2 more minutes and then we will start. Okay, so let's start today's lecture. So, in previous lectures, we studied the basic properties of materials and we looked at the optical response of electromagnetic waves when it interacts with metals. And also, we saw that what happens when light is incident on periodic dielectric structures. Periodic dielectric structures, and for example, for crystals, we saw that if we have a layered medium, then what will be the reflection and the transmission when the light will interact with the layered materials. So today we will focus on what are known as metamaterials and metasurfaces. So metamaterials are artificial. So metamaterials, these are the artificial materials that have been created, or there is no existing natural animal. So, no existing, no existing natural animal. So, to understand metamaterials, we can just have look at epsilon and mu quadrant. So, you can see that on the x-axis we have the permittivity, and on the y-axis we have the permeability. So, we uh, epsilon can, so our permittivity can have range from negative to positive for various materials, and similarly mu can also have range from negative to positive. So at a particular frequency epsilon will be positive. So for example, so if we will see, so for example, permittivity is positive for electrics and it is negative for metals or some of semiconductors. So we have some materials which can exhibit the magnetic response also. So in the previous lectures, for the all materials, we considered permeability for the materials is one. Okay, so we consider the permeability for all the materials mu is equals to earlier lectures. Okay, so if you will see the first quadrant, in the first quadrant we have dielectrics, permittivity, permeability. Both are positive. We have the and in the second quadrant, this is my first quadrant, this is my second quadrant. So in the second quadrant, we have the epsilon is in the first quadrant, epsilon mu both are positive. In the second quadrant, we have metals and doped semiconductor where permittivity is negative, but permeability is positive. In the fourth quadrant, next case is where permittivity is positive, but permeability is negative. So it is termed as magnetic lambda. This will occur. This will occur in some negative materials like iron or cobalt, and it will occur. Example: iron or cobalt, and this occurs at RF frequencies. And in the third quadrant, where epsilon and mu both are negative. In the third quadrant, epsilon is negative, and the permeability is also negative. So in the third quadrant, there are no naturally available materials for this. This is the artificially engineered materials, which we call the metamaterials. So we have to design our structures, design, fabricate our materials such that we can have the permittivity as well as the permeability negative. And there is no such material, natural material material is inherently which has inherently these characteristics, that is permittivity and as well as permeability are both have. So these is artificially engineered materials which we call as metamaterials. So first we will see what happens in a regular material. So we are assuming that plane wave is incident on the material and E is equals to exponential minus exponential iota k power minus omega. So what will happen is plane wave is incident. So if we substitute RMS to it will take curl, we can write K cross C. So this is step first. Then K cross C is equals to omega mu h. And similarly, if we take curl for magnetic field, we will get the K cross H is equals to minus epsilon into mu into epsilon. So we can write we can write the magnetic field in terms of electric field that H is equals to K cross C upon mu epsilon. And when we will take the time average of power flow, then we will get the S is equals to 1 by 2 real part of E cross H. So where S is the pointing vector. So what does pointing vector represents? So pointing vector pointing vector represents the direction of energy propagation. Okay. So here when we will when we will solve for the pointing vector, we have the value E cross H. So for E cross H is equals to we will substitute the value of H here. So E is cross K cross E upon mu naught. So this is the form of A cross B cross C. So we have sorry. So we saw that if we will substitute the value of this E cross H cross. So this is A cross B cross C. The formula is B A dot C minus C A dot B. So if we will solve for E cross H, it is E K cross E upon mu omega. So we will get the B A dot C. A dot C cross E podcast square by mu omega minus C. A dot B. So E dot K. And we know that E dot K is equal to E dot K is 0. So what we got, E cross H is equals to E mod cos square mu epsilon. And similarly, we can write same term for H mod cos square A upon epsilon. Okay. So what we saw from this, that S is in the direction of K. So this is the case when we consider the regular material and a plane wave is incidentally on the material. And when we find out the pointing vector for that, we found that pointing vector is in the direction of K for a regular material. So you can see that E cross K, and here H is, and here X is in this direction, in the direction of. So for a negative polarized material, epsilon and mu both are negative. So if the epsilon, if we solve this for that, so E cross H is equals to C square K. So suppose my epsilon is negative, so here minus, or my permanent is negative, there will be a minus sign. Okay. So now S is in opposite direction. Okay. So you saw that K is in this direction, but your S is in this direction. So now E, H, and K follows left hand rule. So these materials are also called left handed. Okay. So the fundamental way in which, so now we can say that the fundamental way in which the electromagnetic energy propagates is changed, and that has a tremendous application. So what are the negative index materials? So uh, this was first proposed by Professor David Smith at Duke. So we saw that. So earlier we studied that Lorentz oscillator models explain the resonances, and from the absolute quadrant we saw that epsilon is negative for the matters and dot semiconductors. And where can we have the negative mu? So there are these magnetic resonators that are, we say that is spectral resonators. So in case of spectral resonators, we can have, we can engineer uh, permeability as negative. So for that, mu is not exactly equal to 1. So in the previous cases, when we were considering the law, when we explaining the resonance using Lorentz oscillator, we are considering mu is equal to 1. But now it would not be the case. So, and metamaterials, how can we prove? So this can be engineered This is the engineered arrangement of the meta atoms. So there are several examples of metamaterials. So first of all, so when this field started, at that time, at that time, uh, because it started with the RF frequencies. So where we can have the large structures and the frequency around 10.5 gigahertz. So for that case, initially designed. Then, so these were the split ring resonators. It is of the shape like this. One like this. So these are called double split ring resonators, one inside the other. And secondly, in the visible region, obviously, if I'm moving from RF to visible region, the structure we have to scale our structures. So, if suppose if I'm working in the RF frequency, the structure size can be the micrometer range, like 80 micrometer, 100 micrometer. That will be easy to fabricate. But if I will move to the higher frequency region, then I have to scale my structure accordingly, and I have to go into the nanometer size or 1 micrometer size. That is hard to fabricate, but yes, people have done this in the past few years. So these are the paired nanos. So we can tune our structure such that we can have the epsilon and mu as negative. And the next example is fishnet structure. This is also for the visible wavelength, and now the size of the structure was approximately 740 nanometers. So these are the examples I'm happy to have fabricated in this. So now what is the physical interpretation of the negative index? So you will see that in general Snell's law, if the light is incident, you have two medium. Here we have the theta incident. We have the theta incident, and we have the medium where epsilon is greater than 0, mu is greater than 0. So the light, some of the part light will reflect, and some part of light will reflect. So this is theta t, and this is your k direction. Okay. So from the Snell's law, we can say that. So now we can see that if we have the medium which have the permittivity and the permeability both in positive greater than 0, then the reflected light will bend towards the reflected light will bend towards the. So we know that according to the Snell's law, tangential component is continuous. So we have angle sin theta 1 is equals to n to sin theta 2. So then the next case, if you have the negative index, that is epsilon is lesser than 0, epsilon is lesser than 0 and is also lesser than 0, then what will happen? Then you saw that the light is coming like this. But it is, but the reflected light will bend away from the curve. So bending is away from. So we there is this is one experiment showing that if we have what maybe some liquid medium and if you drop one pencil or a straw in the medium with positive, like just if I'm considering water and then in the water we have epsilon and mu greater than 0, then the light will take then the light will bend like this. Okay, and if we have m is equals to minus 1.33, then the straw will bend. It will look like the bending is away from the opposite to the opposite to the case of the positive perpendicularity. So, where are the implications of this negative text materials? So, in the optical cloaking stage, so in radar, if you want that the reflected ribbon, the light after incidentting with the surface will come back towards us. So, we want uh, for radars, we can use such for safety purposes, and we can fabricate the super lens and hyperspectral lenses using these negative index materials. So, how can we define them? The negative index materials in terms of the formula. So, mathematically, n square is equals to absolute mu. So, when we will take the under root of this, so we will have both positive and negative values, n is equals to plus and minus epsilon. So n square is equals to epsilon naught, n is equals to plus minus epsilon. So if the epsilon you are positive, then we were considering only the positive value. So how can we define the bending away from the normal? So we know that momentum has to be conserved at the interface. So the tangential component is going to be continuous, and then the overall wave vector has to be opposite. So, so the only way that can happen is this only that is bending towards away from. So we can show that only way propagate in a negative index medium if it bends this way. So let's consider if we have two reflective indices. So epsilon is equals to, so suppose epsilon, if I'm considering epsilon is equals to minus 1, I'm considering epsilon and mu both are complex. Mu is equals to minus plus delta 2. So this both epsilon and mu will exhibit the passive response, and if I will do the epsilon mu, then we will get this minus 1 to delta 1 into minus 1 plus iota delta 2 under root, and we are assuming that delta 1 and delta 2 correspond. So we can write it at epsilon root epsilon is equals to plus minus 1 minus item delta 1 plus delta 2 1. So if I will consider the positive root, so what does it mean? So a positive root means a material which has some gain, but there is no gain, right? So we can't consider the positive root. So because I have a passive medium, so it if light is interacting with the medium, it can't amplify without any gain. So the positive root we can't consider, and the negative root means there is some losses. We are considering passive medium, so we have to consider only a negative root. So it means n is equal to minus of epsilon u. If so, we have to consider the negative root of reflective index under the condition you have the epsilon u both are negative. Understood? So then we saw that the what is the landscape of optics. So what are the different metamaterials in photonic crystals? How we define on the basis of the landscape? So there are three cases. If my periodicity or A let is constant, it is constant. Periodicity A. There are three cases. If A is very very less than lambda, then we will say it's metamaterials. So my periodicity is very very less than unconsidered wavelength. Then it will come under the case metamaterials. Then and we have to describe our system using the effective medium description using Maxwell equation, epsilon conductivity and impedance, reflective index and impedance. Okay. So then if my epsilon is comparable to the lambda, then my structure will so properties will be determined by the diffraction independence and the examples are photonic crystals and the reflection optics. And the third case is when we have the case very very greater than lambda. So then we can find the properties using geometrical optics and ray tracing. So for example, reflection, reflection. Okay. So our goal is how can we realize an equilibrium. So we realize the equilibrium by choosing the negative root of mu when epsilon are negative. Since natural media rarely gives permittivity is equal to 1 in optics, we engineer structured atoms whose collective subwavelengths are equal. Use the target permittivity and the permittivity. So whatever we want, we can get. So now we will go into more details of the negative index theory. So we need to engineer the electric and magnetic response in order to achieve a negative index. So how can we do that? So if we will look at the basic optical properties, what we studied in the previous lectures, then the material constant were essentially defined by the type of material, geometry of the structure, and we will be patterning into. We will see into nanoparticles how the particle size was affecting the optical response. So here we will address that how can we actually improve the metallic properties. So if we take the first example, if we take the simple array of nanowires. So the geometry is we have a metallic cylinders. These are periodically arranged. Okay, and the wire is along the axis, which have the periodicity of A and the radius is R. So we can think also in the X line. So these are arranged in the XY plane in periodic lattice and it can be cubic. So this structure was analyzed by the Professor John Fenton. So it was in the context of RF frequency propagation, and at that time we were calling it artificial electrons. So we want to engineer the dielectric response. So for fields polarized along the wires, we consider that the electric field is parallel to the direction. So the our medium will behave like a road matter. So we consider the fill fraction. So what is fill fraction? So in the fill fraction, what is the matter fraction in units? So if I am considering that in x and y, it is it's a cubic structure. So I will consider the area of the sphere, and it's a cylinder. So the cross section will be the circle. So my fill fraction will be the area of circle divided by the area of the cube, that will be given by the pi f square by a square, and the effective field electron density will be given by an effective is equals to fill fraction into my conduction electron density within the bulk, that is defined by the M. So here, what will happen? The wires will have some self-inductance which will increase the effective electron inertia. That is, effective mass will be greater than the original mass. And so we have considered two terms, that effective electron density in terms of the initial electron density times the fill fraction, that will be my effective electron density. And one more aspect is that electrons are not yet really entirely free to move because there is a self-inductance associated with the nanowire, and that causes the electron to behave as if it has a slightly electronic effective mass. So we have to consider the effective mass in spite of the original mass. So so the entire medium, let's say wires, consist of wires. These are arranged in lattices, going to be effectively behave like a model. And the effective plasma frequency has two terms. One is effective carrier density, and the other is effective mass, which are different. So the expression of the plasma frequency will be omega T effective. What it will be? It will be so earlier for bulb we were N is equal to M epsilon. So here it will be omega p n effective is scalar by M effective. So here we will substitute the formula of N effective is equals to fill fraction into N, and M effective will be M. Yeah. So it will be very lesser than the plasma frequency in bulk. We will consider some examples regarding to this. We have some problems regarding this concept. Uh, P bulk. Huh. So with these parameters, we can calculate the plasma frequency, and it's clearly anisotropy. So similarly, there are various examples that we can consider the, like if I'm considering the silver, then the effective density of the charge carrier density, the carrier density of the silver is different, and so we can solve the Maxwell equations and can calculate the Poynting vector electric field and magnetic field. So the next part is so, so the next I want to discuss is uh, why the double, why do we consider the double slit resonators? So earlier, so we know that the split ring resonators we were using to make absolute negative. So earlier we were doing like this. So this is your single splitting resonators. But we saw in the previous lectures that in this case we have we have only the electric dipole, and it is dominant. So there was magnetic dipole, but it was very weak. So the mainly the component was the electric field. So but when we are considering the double splitting resonators, then we will have we will have the capacitance associated with gap, this gap, and also due to this gap over all over the system. Okay, so what will happen? So magnetic dipole will dominate. So how are we considering these two SRR? So we are considering two concentric. So a single SRR has a strong electric dipole across its gap, and so if we have electric dipole, there will be induced magnetic response, but the effect is very weak. Then we will consider the two concentric splitting resonators with opposite gap position. We can choose different shapes. We can choose this shape. We can choose the rainbows. So what will it increase? It will increase the coupling between the rings. It will increase the capacitance. That will that will increase that will decrease my resonant frequency, and it will give me the strong resonance at lower omegas, and it will cancel the electric dipoles such that my magnetic dipoles can dominate. by magnetic and it will preserve the magnetic mode. So magnetic resonance will be excited only when the incident field drives charge across the gap. So there will be two things. One is capacitance and other one is inductance. So changing changing the gap between by changing the gap between the resonators, we can tune our capacitance. So magnetic resonance will be excited only when the incident field drives charge across the gap to form a closed current flow, and our gap will be broken by the displacement. So suppose I want to excite. So if I have this resonator, so if I will incident, so if I will incident my light along Y polarized, then only this dipole will incident. So then only the charge is plus negative. And if I'm incidenting such light as polarized, then there will be no loop. So there will be no formation of dipole and hence no magnetic resonance. Okay. So how can so initially we started with the resonators at very low frequency, that is RF frequencies. So how can we scale our frequency by changing the frequency? So we can do by shrinking our splitting resonator feature size. That is, we can change the gap, we can change the line width, we can change the ring size, which will increase the resonant frequencies. And so first we had the structures up to millimeter scale. That the frequency was in gigahertz, and then from gigahertz we moved to terahertz, and we were fabricating structures by using the lithography, photolithography, and then we moved from terahertz to near IR, where the size was in the order of nanometers. So for this we use high precision instruments like electrolithography, laser writing, using that we can fabricate the structures for the visible frequency. So, but at optical frequencies, achieving clean magnetic resonances is hard because of higher losses, fabrication potentials. So these were the challenges. So what are the key takeaways from this? Like an isotropic is the route that is most designs ill tensor. Like in X and Y direction, permittivity is different. So sometimes permittivity can also be, but the mainly we are considering structure for which the permittivity is different in the X and Y direction. And effect we will be consider the defective medium condition where our the cell size like A that is constituted very less than lambda justify homogenization. But if A will be comparable to lambda, then the band structures and diffraction effects will appear. So, and in terms of losses, there are ohmic losses, ohmic radiation that will broaden my resonances. Means broader resonance amplification will increase, and it will decrease the uh, frequency window where both mu and epsilon can be negative. And how can we design such structures? By changing the fill fraction, by changing the gap, by changing the ring dimension, by changing the periodicity, that is the interring or interring spacing lattice period, so that we can tune my resonant frequency and sign or magnitude of epsilon and my bandwidth. Okay, so This was the example where we are considering the planar matter dielectric composite. So we have a silver and Si2. So we are assuming that the periodicity where A is very very lesser than lambda. So we know that F1 plus F2 is equals to 1. Okay. So we know that the tangential component is parallel component. The electric field will be equal for both the materials. So E is equals to E1 is equals to E2. So, but when we will define our displacement current, D is equals to F1 D1 plus F2 D2. So D is equals to epsilon E. So epsilon E is equals to F1 epsilon 1 E1 plus F2 epsilon 2 E2. Okay. So this is, so if I'm considering that epsilon parallel is equals to epsilon F1 epsilon 1 F2 epsilon 2. This, so we can say that parallel, the permittivity in the parallel component is just the weighted average. Okay, and the perpendicular component will be epsilon 1 into epsilon 2 f1 epsilon 2 plus f2 epsilon. How it is defined that? Because 1 upon epsilon effective perpendicular is equals to f1 by epsilon 1 plus f2 by epsilon, because we know that in the perpendicular direction of displacement current d is equals to d1 is equals to d2. So epsilon effective perpendicular will be f1 e1 plus f2 e2, and d by epsilon effective is equals to f1 d1 by epsilon 1 plus f2 d2 by epsilon. So now this d is equals to d equals to d2 will be cancelled. So we can, the electric permittivity here is an answer quantity, and we can, and it is given by epsilon parallel 0 0 0 0 epsilon parallel 0 x and y direction parallel components, it will be same, and it will be different for the perpendicular direction. So here it's one example that if we consider permittivity epsilon 1 for silver suppose -10, and for SI it is suppose 1.45, or some other material which have the positive permittivity that is 0.25, and filling fraction is zero point 0.5. So we can, if we know such, if in these returns, we can easily calculate the permittivity in the parallel and as in perpendicular direction. So similarly, how can we engineer the magnetic response by using the introducing the circular current in the structures given by the Lamb's law, and so we can have the rings, split ring resonators in terms of square shape, ring shape, where the gap will introduce a capacitor and it will give you an inductive response, and the resonant frequency will be given by omega naught is equals to 1 by root S. Okay, so this is what I told you already, that double split ring resonators has better magnetic response, and we have scaled this. So okay, so next we have the example coupled nanorods. So here we have a pair of nanorods which will exhibit the magnetic response, and so the reason it exhibits a magnetic response is, if we will think about this, the in magnetic field in this direction, in the perpendicular uh, to the axis of nanomodes, and we can have a circulating current going in these roads, and then the displacement current at the gap. So basically, this circulating current will give us the magnetic response. So, so this displacement loop will give rise to magnetic response, and the magnetic field will be confined between these two roads. So the simulations have already done this. So if If the nanorods, this is about the individual nanorod, but if we arrange in a periodic arrangement, periodic lattice, and I can create a mathematical. So then how will the nanorods behave? So first of all, in the dimensions of nanometers, it is very difficult to get rods like this, and that's why uh, people started fabricating in the micrometer range, or we started like in this shape. Like we have a spacer here, we have a continuous layer silver Al2O3 silver. So selected the we have fabricated this in the glass substrate. These are easy to fabricate using lithography techniques, and we have a strip of panels with Al2A3 spacer layer, and we can confine the magnetic fields in the gap. So in this material, we can have okay. So we can see in this simulation that H, our magnetic field is along the strip, and electric. So we have the T and TM modes. If I'm considering the transverse magnetic mode, then the magnetic field is along the strip. If I'm considering the transverse electromagnetic field, then the electric field is along the strip. So our pair of nanostrips will support both electric and magnetic resonances in TM polarization, and but T polarization will excite only electrons. So in this figure we can see that in TM modes there is a change. So we can see that by changing the fill fraction, or by changing the parameters, we saw that there are change in my TM mode, but there is no change in TE mode. So for TM incidence, along if I am to look at my cross section, I am looking at the side view of this. Okay, side view of uh, and if when I have magnetic field along the stripe and these electric along the strip, so I can look at these structures, and we can see that two types of resonances are excited. So when magnetic field is along the strip, we can say the circulating displacement current like this. Here arrow represents the displacement current. Okay, so there's a strong confined magnetic field, and this is basically the view reason. This is the magnetic field. Okay, this is the magnetic field. So this is confined magnetic field between alumina into the in the metal. So why do we choose alumina? Because it has slightly higher dielectric constant compared to the silicon dioxide. So if we studied at that, if you have higher contrast, then we will have better confinement. That's why we choose alumina. So we have silver, uh, metal, and Al2O3 between them, uh, and this is a magnetic response. So this is another example where negative index are near IR frequencies. So the size has reduced in the nanometer range. So we can see that refractive index is negative for the wavelength at 1.5 micrometer. That is a very small window. Okay, so from this we move to relative refractive index and visible frequency. So we fabricated the fishnet structure where there we have metal dielectric method, and we like the people got the negative refractive index for the wavelength range between 720 to 760 nanometer, And if we are considering, uh, so there are two cases. If we have the example of active negative index optical material, that active means if I'm pumping, if I'm giving the extra energy, some material with some gain, then without pumping, index is not negative. So it's just that we need not to fabricate the structures again and again. We can just we fabricate the structure and we can just tune my frequencies by pumping the structure. And if I'm pumping this, if I'm pumping the structure, so with pumping we can have the negative absorbance for the range between 720 to 740 nanometers. So here we have the negative refractive index and negative absorbance for a range with the bandwidth of 40 nanometer, 40 or 20 nanometer. So where we can use this, we can use it for to fabricate the perfect lenses. So with by using this, uh, in the previous lecture we saw that the evanescent waves decays in amplitude. But if we will fabricate using these such materials with negative refractive index, so the evanescent wave will grow in amplitude and it will perfectly image an object at cloud distance. So the other examples are near field superlens. So same concept will work and we can generate the holograms with this, and then we can fabricate hyperlens using negative refractive index materials. So we will take the 10 minutes break here, then we will move further. Okay, so let's let's resume. So next is beam theory using plasma antennas. So for example, we have a plane wave in which a plane wave which is incident on the surface or an interface, and we want to bend it at a particular angle. So how can we realize that? So in the traditional optics, if we consider the fundamental principle. So what were the fundamental principles of the wave propagation? So it was according to Huyson's principle. So the fundamental principle of wave propagation is Huyson's principle, which says that every wavefront introduces secondary wavefronts, and then those secondary wavefronts propagate in a spherical fashion. So, for example, this beam will introduce a secondary wavefront here, and that will start propagating its, like wavefront like this, and another point will again contribute another secondary. Okay. So all of these wavefronts will propagate, and eventually it will have an overlapping, and the overlap of the phase fronts is what defines the direction of the beam, and that's how beam propagates at an angle. So how can we achieve that? In the traditional way, the doing the standard thing, like we have to create a structure which is a triangular piece like this, and let's say if we are shining light in this edge, and there is a piece of glass. So the phase fronts will propagate slowly, and the light will tilt a little. So what's the reason that they're slowed down is because there is a thicker piece of glass, whereas in the other side the phase front move faster, and the envelope, we can see that the overall envelope of this given reference will actually be tilted in this fashion, and then the beam points. So this is the fundamental way of thinking. This is how the prism does the bending of the light. So, but in practice, we cannot in practice create a continuous edge, or we can give a phase gradient. So, if the wave will propagate like this, it will have a phase of 2 pi, 0 to 2 pi. Suppose if we have a continuous gradient like this, let's say gradient which is 0 to even 10 pi or 8 pi. If we have such a phase gradient, I can simply at 2 pi, wrap at 2 pi, and then we can create a triangular phase triangular profile like this. Okay. So if we go from 0 to 2 pi, come back to 0, and then 2 pi, and so on. So this will be the same effect as having phase profile, which is going from 0 to 8 pi. Like 0 to 2 pi, come back to 0, and then 2 pi. So total of 8 pi, phase profile will be same, directly going from 0 to 8 pi. These two are equivalent. But how can we create a phase triangle which is like a triangular fashion? So we already studied the plasma. Sorry. We already studied the harmonic antennas or the sphere that the splitting resonator. It's also the one component. And then we looked at the triangle, the board shape. So we can consider this simple robot. And this is a perfectly electrical conductor. So if we have such a magnetic rod and we will fix the wavelength and that length of the rod, then we will see that it is obviously if it has a rod, it emits a resonance. And the resonance, suppose let's say it's 1.5 or 48 meter, we have the resonance. And then there is a resonance associated. With this resonance, there will be a phase change. So just like in case of DC resonators, you will have a phase change across the resonance, and the phase values will be from pi. So here we can see that from pi to point 2 pi or so, across the resonance we can see the phase variation. So if you arrange such antennas, let's say one small antenna, bigger antenna, array like small, big, then big, then big. So we can change. We are introducing different phases across the different sizes of the nanotubes. So when a light will essentially it will give my triangular phase front. That is ideal phase front for the phase gradient. We can sample it with the harmonic antennas. So we can sample phase gradient with the harmonic nano antenna. This is the idea that we have completed. So with so the bulky optical elements can be replaced by the ultra thin nano antennas. So it's as fundamental as revisiting the Snell's law. So the example here is if we have Snell's law already, and here we have two interfaces anode and anode. The light is incident from the one theta I and moving it is going to the medium. So N2 sine theta t equals to N2 sine theta I. So this is the standard thing. But suppose now we have uh, in addition to this standard case, what we have a phase gradient at the interface. So here, what if we have a phase gradient, then what will be the case? So then we should say that the gradient of phase divided by the gradient that is d phi by dx. So if we have the antenna, we can create the phase and there is a periodicity associated with this d phi by dx. So what will happen? So we know that this is like momentum and there is a discontinuity in the phase at the interface. So we can write the same momentum calculation and we have the momentum in the first medium, in the second medium, and then at the discontinuity at the interface, which is our boundary condition. So just like we have the two electric fields in the two media, so we can write it n2 sine theta t minus n1 sine theta I is equals to 1 by k naught d phi by dx. So on the right side, it should be dimensional. So we say this is gradient of phi is d phi by dx. So lambda by, so k naught is 2 pi by lambda, so 1 by k lambda by 2 pi. So now this is our generalized expression for Snell's law. There is some bit of There are various examples for this, like how can we create a phase discontinuity with the plasmonic antennas. So we have the initially we considered a single rod, then if we are bending this rod, then we can have the two more symmetric mode and anti-symmetric mode. In the symmetric mode, the electric field is in along the rods, that is the lambda effective will be equals to 2h, and it's a positive and negative. And when in case of anti-symmetric mode, the electric field is along the perpendicular direction from the one node to the another node. And the effective lambda effective is equals to the h only. So we have to we can so how are we planting our light, and how are we which parameters we are doing, which mode we are considering, either symmetric mode or anti-symmetric mode, the phase will change. And here it has been shown that with the phase is changing. The phase is changing as a function of h, height of the row, plasmonic antenna. In this case, they have changed the geometry. They have, in this case, we can see that we have a arrangement of the nanorods in the x direction. It has rotated by a sun. It is bended by the sun, which will introduce a gradient change in phase, but in the y direction it is same. So we can also change in the y direction. It will have a different effect. So it was large in size, but when we did it in near IR range, say the structure size had reduced, and it's in the case of nanometers. So these are the harmonic metasurfaces we can also use to generate the holograms. And these are the examples where we can generate a color palette using by designing the different heights of the disc, uh, which is made up of gold or silver, and we can we can encode a different images, such that in the first example you can see that there are different colors and different shapes. It's a face of a woman, which is encoded using the structure arrangement of the plasmonic antennas, which has some phase associated with this. Similarly, this painting is generating different colors, and then so this was all about the lectures. Now we will move on to the assignment. So, the first question is for a bulk reactive material where we have the permittivity is greater than zero, as well as permeability is greater than zero. The pointing energy flow, pointing vector S, and the propagating vector K are, so the options are in the same direction, in the opposite direction, or equal to each other at 30 degree to each other, at another minus 30 degree to each other. So we have a case. Okay, so epsilon is greater than 0, mu is greater than 0. We saw that K cross E is equals to omega mu h is equals to minus mu E. So S was 1 by 2 real part of E cross S, and here we had S is equals to mod of B square to omega mu. So the if the mu is positive, mu is greater than 0, Then my pointing vector that I am pointing vector is in the same direction, 2k. So S is in the same direction. Next question. Consider a multi titanium silicon composite as shown in the figure. So here we have the layers, alternating layers of titanium and silicon. So the permittivity of titanium is epsilon of titanium is minus 4 plus 12 pi and epsilon of silicon is 15 plus zero point 0.2 at a wavelength of 600 nanometer. Okay, the thickness of each layer is much smaller than the incident wavelength, and FTI, FSI are the field fraction of titanium and silicon respectively. So these are the common details for question second to fourth. And then the question is the in plane effective permittivity. The in plane effective permittivity for a fill fraction of titanium is 0.6. So we are given that FTI is equals to fill fraction of titanium is 0.6, and so we know that epsilon permittivity in the permittivity in the parallel plane is the weighted average. So epsilon what is epsilon parallel f of t epsilon of t plus f of silicon epsilon of silicon. So simply if we know the f of fraction of titanium, we can find out because we know that f of ti plus f of si is equal to 1. So from that we can find out the FSI is equal to 1 minus fraction of titanium. Okay. So it is 0.6 fill fraction of Ti and epsilon of Ti was minus 4 plus 12 by plus 1 minus 0.6 is zero point 0.4 is equals into 15 plus zero point 0.2. So if real part, if I consider real part, that is 0.6 into minus 4, that is minus 2.4 plus zero point 0.4 into 5 6. So real part is 3.6. Imaginary part is zero point 0.6 into 12 plus zero point 0.4 into zero point 0.2 is equals to 7.2 plus 0.08, which is equals to 7.2. So the overall is equals to epsilon permittivity in parallel direction is equal to 3.6 plus 7, right? 3.6 plus 7.8, right? So the correct option is the last option. Next question is the effective permittivity in the direction of propagation of the incident wave for a field fraction FTI is equal to zero point 0.6. So, so we know that permittivity in the parallel plane is 1 by perpendicular field fraction of tie 1 minus f type upon epsilon. Okay, so ft is equal to 0.6. So how will we solve this? It will be so it will be 0.6 by minus plus 12 at plus zero point 0.4 by 15 plus zero point 0.2 at. So how can we solve this? 1 by a plus iota b is equal that we have to multiply it by a minus iota b, multiply and divide with a square plus b square. So we can solve this. Zero point 0.6 by minus 4, so what it will be. So this part will be minus 4 minus 12 by 4 square plus 12 square is equals to minus 4 minus 12 iota by 60 is equals to minus 0.025 minus 0.075 iota. Similarly, 1 by epsilon psi is equals to 15 minus 0.2 iota upon 15 square plus 0.2 square. 15 minus 0.2 iota is equals to 0.067 minus 0.008. So now we have multiplied by f of epsilon pi. So 0.4, 0.067 minus 0.026 minus 0.00035. This is all math. We can easily solve that. Epsilon perpendicular is equal to minus 0.015 minus 0.0455 plus 0.026. Similarly, here also we have to multiply TIF. TIF is 6. Okay. Yeah, so after this calculation, I got the 0.026 minus, so we got 0.0116 minus 0.0453. So now for finding the absolute permittivity, it will be 0.0116 plus 0.0453 after upon 0.00. Okay, so it will give us 5.31 plus 3.6. So this is the final answer. So it is a 5.3. First option, the correct answer. It's just the calculation. And the next question is the effective permittivity in the direction of propagation of the incident wave for a field fraction f of I is equal to 1. So we know that FTI plus FSI is equal to 1, and if it is given that FSI is equal to 1, that is filling fraction is equal to 0, then whole surface like medium is pure silicon. So the epsilon permittivity is silicon permittivity. So it's just that 15 plus 0.28. The next question is consider a two-dimensional periodic metallic wire array embedded in an electric cable. The radius of the wire is r is equal to 5 micrometer and periodicity is E is equal to 40 micrometer. So, and the schematic of the unit cell of the metamaterial is shown in the figure. An electromagnetic wave is incident on the material such that the incident wave is propagating in the x direction and polarized in the z along the z axis. So the question is we want the effective Fourier concentration of the material is. So we are provided NAG is equals to 5.8 into 10 raised to power 28 per meter cube. So we are given square units. For a square unit, fill fraction. So the area of circle is pi r square and the area of square is a. So this is the fill fraction. So the r is equals to 5 micrometer. So r square is equals to 25 into 10 raised to power minus 12 meter square, and a is equals to 40 mm. So a square is equals to 4 into 10 raised to power minus 2 square is equals to 16 into 10 raised to power minus 4 meters. Okay. So now f is equals to pi into r square and 1.6 into 10 raised to power minus 3, which is pi into 1.5645 into 10 raised to power minus 8 is equals to 4.9 into 10 raised to power minus. This is our fill fraction. So now we want to find out the n effective. So which is we know that f n original. So n silver. So fill fraction is 4.9 into 10 raised to power minus 8. And the n silver is given that 5.8 into 10 28 cube. So n effective would be 2.85 into 10 raised to power 22 per meter cube. So option B is the correct answer. Next question: the plasma frequency of the material is approximately. So we saw that the plasma frequency in the bulk will be very large as compared to the in this case for the material case. So omega p is equals to n effective e square upon epsilon naught. So m effective we are given is 2.1 into 10 is to power minus 25 kg. So what is n effective? And effective we find out that 2.85 we have to we just calculated the previous question 2.85 into 10 raised to power 21 square and if an effective into p square. So an effective we calculate 2.85 into 10 raised to power and electron is up to 1.6 into 10 raised to power minus 19. It will give you 7.31 into 10 raised to power minus 17. Now epsilon naught into n effective is equals to 8.85 into 10 raised to power minus 12 2.1 into 10 raised to power minus 2 is equals to 1.85 into 10 raised to power minus 36. So omega p is equals to 7.31 into 10 raised to power minus 1.85 into 10 raised to power minus 36 1 by 2. So that will give me 6. It will give me 6.26 into 10 raised to power 9 radian per second. So now it is an angular frequency. Now I want the plasma frequency Fp omega p by 2 pi. So 6.26 into 10 raised to power 9. Since it is in so its plasma frequency is omega p only, but the units we can see there are some terms of terahertz. So we have to find out in terahertz or giga frequency. 9.6 6.26 into 10 raised to power 9 upon 2 pi. So which will 9.98 into 10 raised to power 8, which we can write 10 raised to power 9 hertz, and which is equivalent to 1 gigahertz. So the correct option is third option, 1 gigahertz. The next question: plasma frequency of the metamaterial is approximately. So we want to find the plasma frequency. So we didn't. We are given. We have to consider the bulk plasma frequency Fp bulk. Okay. So we saw that omega p is proportional to n, directly proportional to n, and inversely proportional to effective mass. So Fp meta upon Fp bulk. We can write n effective by m effective into m bulk n bulk. So we will substitute the values 2.84 into 10, 2.85, it is 2.85 into 10 is for 21 upon 2.21 into 10 is to power minus 25 m bulk 9.1 into 10 free electron mass 9.1 into 10 is power minus 31 and n bulk is 5.8 into 10 is to power 28. So, so after calculating this, you will get 2.126 into 10 raised to power minus 30, and we will get the 4.612 into 10 raised to power minus 7. So now the plasma frequency of the material will be 4.62 into 10 raised to power minus 7 into plasma frequency in the bulk. So the option 1 is the correct answer. Now the next question is given below are two statements regarding the split ring resonators. uh, Used to generate the magnetic response at terahertz frequencies. The statement first is double SRRs are preferred over single SRRs for magnetic material designs, and the statement second is double SRRs suppress the fundamental electric dipole better than single SRRs, thereby providing dominant magnetic response. So, during the lecture, we saw that in the in the signal in the single SRR, there is a strong electric dipole, and due to which there is an intense magnetic response. which was weak. But in case of the double SRM, the first statement is correct, the double SRM. In the second, there is a capacitance C1, C2, and because of this C3, and it will suppress the fundamental electric dipole activity. In this case, it will have the dominant magnetic response. So this both statements are true, and since in case of double splitting resonators, it suppresses the fundamental electric dipole. That's why we prefer the double SRM. So S statement second is the true explanation for the uh, so second statement as the correct option is statement S1 and S2 is true and S2 is the correct explanation for S1. The next question is the generalized Nernst law is given by theta I theta t of incident NINT reflective index. Okay, so just so we saw that uh, generalized uh, generalized law. So standard Snell's law is Ni sin theta I is equals to Nt sin theta t when there is no phase gradient at the interface. So now we want to find the generalized Snell's law where we have some phase gradient at the interface. Okay, so in this case, in the lectures we saw that it will be the t sin theta t minus ni sin theta I is equals to, here it was k naught inverse d phi by dx. So k naught is equals to 2 pi by lambda. So 1 by k is equals to lambda by 2 pi. So the correct answer is, so the n t sin theta t minus theta I is equals to lambda by 2 pi by dx. So A is the correct option. So if metasurface, suppose, so now we were asked about the transmitted wave, okay, transmitted medium. So uh, suppose we have, so we are considering next condition, okay. If metasurface imposes a phase on the reflected wave, same tangential number will give n sin theta r minus ni sin theta I is equals to lambda by d phi by x. Okay, so here we have taken some assumption that the metasurface is locally periodic and hence higher diffraction orders are suppressed. Otherwise, so it's just a general that metasurfaces locally periodic and hence higher diffraction rates are suppressed. Otherwise, some grating event happens. Factor of m 2 pi by lambda, depending upon which is the order of diffraction. So it must be also. Okay. So this is nothing. The next question is given below there are two statements regarding the plasmonic metasurfaces. The first statement is the plasmonic nano antennas confine electromagnetic energy into extremely subwavelength dimension and thereby reducing the overall dimension of the metasurface. And the second statement is plasmonic antennas are lost in the visible region and hence cannot be used for application requiring long propagation distances. Okay, so the statement first, obviously, we are fabricating the nano antennas of the small cell because we want to confine the EM wave in the subwavelength dimension. So the first statement, and also it is also minimizing the size of the metasurface. So first statement is correct, and the second statement. So plasmonic matter. So the plasmonic things are velocity. We know that these are some evanescent decay length. Evanescent decay it is up to a smaller distance of order of magnitude only. So we cannot use for where we require the application regarding long propagation. So both the statements are correct. So the option third is good. And the last question given below are two statements regarding the plasmonic and the electric nanospheres. The first is the electric nanospheres are not limited by the classic diffraction mode unlike the plasmonic nanospheres. But this statement is false. In case of dielectric nanospheres also, we have to consider the diffraction mode. We have to choose the size according. And the second statement is the electric nanosphere can support both electric and magnetic resonances, whereas plasmonic nanospheres only support electric resonances. This is true, we saw that in case of this positive negative. So here the only in case of this there was only the electric dipole outside, not inside. But in case of there was a induced charge and because of in case of dielectric we have the induced charge also. The electric charge induced and there will be induced magnetic field. So there will be both. It can support both electric and magnetic resonances. Both electric and magnetic resonances. So statement one is false and statement second is true. So the option B. So okay, thank you so much. This was all about our today's lecture. So we will see you on the next Saturday.